You know, the personal flying machine, well, it's been a subject of popular imagination since stories of Icarus. Now, in the post-war era, 1950s, 1960s, it was attempted by many firms, large and small, some helicopter makers like Hiller, for example, the flying platform, Bell, for example, with the jetpack. But perfecting personal flying machines, well, that's always been a challenge. I'm with Tarek Ibrahim, he's founder of AirVinci. And Tarek, we're standing in front of a prototype of essentially what will be a personal flying machine. So this is a ducted fan configuration. I understand we have coaxial propellers inside here. Now this is not big. This is what, about 2 meters in diameter approximately?
Yeah, it's 6 feet wide, 1.8 meters in diameter. We wanted eventually to fit in your driveway. We didn't want it a large footprint, which is a problem with aircraft now, is that all helicopters now are super large. So we didn't want something like that. We want something very small and compact, so more useful for more people in dense areas.
Why did you decide to go down this road where so many have tried for so many decades and have frankly failed?
I really wanted to try it for myself. I'm an architect, so I have a master's of architecture from the University of Houston. So built my own car from scratch, built a factory from scratch. And I was like, okay, I've done these, now I'm ready to go on to the next level, the next challenge, and the next challenge was personal flight.
Have you had to teach yourself essentially aerodynamics and design software? There's so many things you need to know to get to this point.
I had to learn a lot, absolutely.
Are you doing this on your own?
So there's a team. There's a team of about 10 people now. Whatever questions that I don't know, I ask my team. So for an example, in aerodynamics, I know that my knowledge when I started out was a little bit limited, so I'd ask my aerodynamics engineers or mechanical engineers, or the same thing with all the fields that this covers.
Let's talk a little bit about this technology here. I'm looking at the duct here is carbon fiber.
Yes.
This is chromoly steel tubing?
Yes.
Okay, yeah, which is welded together. This will form the propulsion unit. There'll be a structure beneath this?
Yes.
Okay.
Yes, yes. So this right now is the first iteration, and it's basically a proof of concept kind of test flight platform. Iteration number 2 or version number 2, it will be all composite, mostly composite.
There's no boom and tail rotors, there's no anti-torque device visible here, so clearly we're looking at coaxial propellers.
Yes.
Coaxial, of course, requires a fairly complex gearbox.
Yes.
And in this case, you have 2 power plants. So 2 power plants. Now, the power plants, are they feeding a common gearbox, or does each power plant drive one propeller?
Both engines are both driving both propellers. So in case you get an engine failure, you don't lose a propeller. When both engines run both propellers, even if you lose an engine, you don't go into uncontrolled rotation.
Airfoils, of course, are critical, and this is an unusual circumstance here because this is an enclosed rotor system.
Yes.
So the aerodynamics are much more complex than this. How difficult was it to design an airfoil to work in this application?
It's very difficult. Now, when you start looking at something that has a ducted fan for hovering, there's not a lot out there. I mean, you can look at a hovercraft, but a hovercraft uses an impeller, not a propeller, which is a little bit different. So we had to design that from scratch.
What sort of airfoil sections did you use, and is it a single airfoil section throughout the blade?
No, so I actually used a bunch of airfoil sections to achieve what we needed to achieve with the engine. The helicopter is a fixed pitch blade design. So to achieve the highest efficiency, you have to use airfoil sections in certain areas so that you can get the most lift according to the RPM that you have.
The prototype here, this is powered by, those are Rotax piston engines?
Those are Hearth.
Hearth,
yes.
Right. Yeah, these are aviation engines. I see dual plugs, so there's dual redundancy in the ignition system.
Yes.
And those engines will be typically used for ultralight aircraft?
They are used for ultralight aircraft. So they're 28 horsepower each, so combined 56 horsepower.
How will a pilot operate this?
So there are control surfaces. So if you would imagine a normal airplane, but you would tilt the airplane 90 degrees so that the propeller is above you, and you're using the elevator and the rudder as your control surfaces. That's how this is operated. So it's fixed pitch, which eliminates a lot of the mechanical complexities with a normal helicopter. So there definitely is going to be an automation aspect of this. There's going to be a computer control with gyroscopes, magnetometers, and all that, accelerometers, to kind of keep it level in flight, and it would also reduce the load on the pilot.
Do you anticipate a ballistic parachute system for this?
Yes, there definitely is going to be a ballistic parachute system installed, and we're also working on other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. Plus, we're going to come up with other safety systems that will allow you to safely fly at low altitude. that even if you're at 100 feet and you deploy the parachute, it will work and it won't crash.
Tarek, of course, the business end of any flying machine is what generates lift, and lift is generated here.
Yes.
Here in the places.
Yes.
Now, this looks like a foam core carbon fiber
Yes.
part.
Yes.
What are your materials, and how are you making these blades?
In this particular case, it is a foam core with carbon fiber on top, but it gets a lot more complicated than that in terms of where you need the stress, how to distribute the stress along the fibers of the carbon fiber and all that. We test for bending, we test for tensile strength, which is caused by the centrifugal force. We test for a lot of things. So this is one of the earlier ones.
Tarek, you're building a flying machine which is not a helicopter.
Yes.
It's not an airplane.
No.
How do you certify it?
We actually have to make the rule. So we have to come up with a new category to certify it, and we're in the talks with Transport Canada to certify that. The long-term goal is that everybody will have one of these, but the entry is probably going to be search and rescue and Coast Guard, and another entry point is skydiving, skydivers.
And what's your anticipated payload for your prototype, or your first iteration?
So first iteration anticipated payload is 260 pounds or 120 kilograms. That does not include the fuel. It does not include an hour of fuel. And you have to do things the right way, because there's no shortcuts in aviation. There's absolutely none.
Tarek Ibrahim is reinventing the notion of personal air transportation here at AirVinci.